So without me speaking any longer, I think it's time that we get our first speaker up. Arnau, if you'd like to come up here. I would like actually to do a quick introduction, if you don't mind.
Sure. Yeah.
If the audience is ready here. So Arnau is not only working within a startup, he also has a past from academia, has a PhD as well in artificial intelligence. And is it since 2015 that you've been working with your startup? Yep. And that is within fashion and AI. And that's the first time we had this theme on stage. So we're really excited to hear your work. So let's please give him a warm welcome.
So, good afternoon. I am Arnau Ramisa from WideEyes Technologies. We are a B2B company that works in fashion, computer vision for the fashion industry. And we work with companies of the type of H&M. And what we do is offer them solutions that use computer visions that try to address their problems. And their problems are mainly that fashion is a primarily visual thing. So fashion is perceived mainly through the eyes. And for their retail e-commerces, these big companies, fashion companies, the best thing they have in order to make their huge catalogs accessible to their customers is, in the best case, a short text description of the product, and in the worst case, maybe only a category type that is associated with this product. So what we try to do at WideEyes, okay, so as I was saying, our purpose at WideEyes is to train deep learning models that can get to understand this kind of products that the fashion companies sell in their stores, and then use these models to perform some tasks that might be useful for them. For instance, very straightforward task that we can do is categorization. If they have pictures of their products, we can say what is the category or what is the type of product that appears in the picture. Then another type of task that is quite interesting to do is similar recommendation. If someone is looking for products, maybe we can offer a few other products that are similar to the one that they are looking at. And hopefully he can find some interesting one among them. And that only using images, of course. And then also, we could extend this to pictures that the customers can take themselves with their mobile phones. Maybe they see something in the street they like, and they take a picture. And they can use this picture also to search for products in these retailers' catalogs. And maybe it's a complete outfit, so they can find a match for each one of the clothes that this person is wearing. Speaking of complete outfits, actually there is another interesting application, which is, given one single product, find complements that can result in a complete outfit and that combine well and then that can be worn in the street. This last application is actually pretty popular and is attracting a lot of interest, both in academia and industry. So in this talk, I will focus on a couple of these applications, and finally, I will share with you our last work accepted at CVPR 2019, just this week. So very good news. So first, I will go into categorization. So categorization is a task for which the first thing that you have to do is basically define a taxonomy of classes, and then you can start annotating images in this taxonomy of classes and train a classifier. However, for fashion, there is one problem, and it is that fashion is a really fine-grained domain. So should you want it, you could have a number of classes that gets dangerously close to the number of training instances that you have in your dataset. That is definitely not a very healthy situation for training classifiers with machine learning. For example, what class would you assign to this image, sandals or wedges? So you could tell me it doesn't matter, just choose one and go ahead. But actually, people really do care about these kind of things, and we have had incredibly heated debates at the office on topics like this one. So then you could say, well, you could use fuzzy classification and say maybe this is 50% sandals, 50% wedges. But that is really not a very satisfying solution and not that practical either. So what we have chosen to do at WideEyes is to, instead of have super fine-grained classes, factorize them into attributes. And that can be done, for instance, in this way. For this dress, I can tell you that this is obviously a dress, that it has transparency, that it has a square neckline, it has straps, it is sleeveless, it has a floral print, knee-length pockets, the material is organza, etc. So they are a set of tags or attributes that apply to this dress, and it's another way to define a very specific class, with the advantage that with these attributes, we can train, for example, floral print using all the images that share the same attribute of floral print. Instead of having to define a super concrete class for this type of dress and then having no training images for it. So these attributes act as a sort of dual space for the classes in which you can express really particular things as a combination of different tags. Okay, so the next thing I'm going to talk about is similar recommendation. And in this task, the purpose is to, using a query image like the one in the left, find a set of similar images in the catalog of the retailer, like the one on the right. However, these similars are not defined in terms only of similar appearance. They also have to be similar in terms of the occasion they can be used in, the style, and the characteristics. So it's a bit more nuanced than just searching for the most similar picture. And you need to have a type of representation that can encode all this information. So for instance, if you have a dress as a query that is a winter dress, you don't really want a summer dress as a response, even if it has a really similar appearance to the other. Actually, in this set of recommendations here, there are a few dresses that are not very good similars for the query one, according to some of our fashionistas. So maybe, can you spot them? Ah, nice. So congratulations if you got them. These dresses, even though they are quite similar in appearance, they all have this floral pattern, they are more or less black, they are more or less short. These ones are for different seasons and occasions and styles. So that is not the kind of thing that the person who searched with this dress was looking for. And we have to train some sort of image embedding space in which the images that we want to return for this query are close by and not the other ones. Okay? And if that was not enough, on top of that, we also want to extend this functionality to these pictures that the people can take with their mobile phones. And these kind of pictures are really, really difficult. They can have really lots of problems, like motion blur, they can have low resolution, bad illumination, and highlights. They can be taken from weird points of view. In general, they might have lots of problems. And additionally, clothing is usually a flexible thing, so you can deform it in any way you want. So there is another layer of problems. And the way in which people usually solve this kind of association problem is to train a network that connects the pictures in the left to their equivalents in the right. For instance, these pants that you can see here have to be connected to the picture of the pants that you have on the other side, which is really different in appearance. And the way to do that is through deep metric learning or embedding networks that can be trained using, for example, the triplet loss. And the triplet loss works in the following way. You feed your network during training a set of 3 images, an anchor, a positive, and a negative. And what the network has to learn is to put the positive close to the anchor by a certain margin when compared to the negative. So the anchor and the positive have to be close. The negative has to be far away, given a certain margin. If you repeat that process many, many times with many different triplets, in the end, your network will have learned to position the images in such a way that when you search using these images in the left, the ones in the positive column will be the most similar to them. Okay, so now I will move to some more practical thing. How are these networks that we train in the research team in the left used by the production team, the people who actually make something that is useful for the companies that request our services? So what we do is we give them the trained model, and they put it, the development team put it in the cloud, in machines in the cloud that are running these models. And the fashion companies then send their request, the pictures on the right, to some kind of image queue that then sends the images to the machines in the cloud to be processed and response returned to them. However, the problem is that in order to have good performance, these deep learning models that we train usually have to be pretty big. And that means that they are also slow and expensive for the company, because we need more machines to run them in order to reduce the latency in the image queue for our users. So it would be good if we could find a solution to make these networks less expensive, less big, and faster. And looking at the recent literature, we found a really good solution, which is network distillation. In network distillation, what you try to do is, given one ensemble of teachers, the ones darker ones, that have a very good performance, but they are really big models, very difficult to train and expensive to use, train a student model, the one on the bottom, which is much more lightweight. And the objective is to have a similar performance between the lightweight student model and the heavy teacher models. So the way it is done is that in addition to the hard labels that are in our training data set, the student model also is trained using the predictions of the trainer of the teacher models. So the objective is that the student can produce class distributions similar to the ones produced by the teachers. And this is a much richer supervision signal than just the hard classes or the hard labels on the training data, because in addition to knowing which is the right class, the student is seeing what are the reasonable mistakes it can make. It can see a probability distribution over the classes. So it can learn a lot more than just with one single hard label. And both in the literature and in our own experience, with this approach, the student model can benefit a lot and get a much better performance than what it could have gotten if it was only trained using the hard labels in the data set. And often it can get to the performance of the teachers or even to a better performance sometimes. Sorry. And this is all great, but there is a little caveat here. And it is that network distillation theory is only developed for classification networks. So it is great for our attributes, but not so much for our similar search, in which we use an embedding network that is trained using deep metric learning. So what we did with our colleagues at the CBC is to extend this distillation theory to this other type of training, the deep metric learning training. And in this type of networks, as I said before, what we want is to produce some kind of image embedding in which we can project the image to a vector space and then performs nearest neighbor search or similar there. So what we care about really is this embedding space. So we thought about it, and we found two different ways in which we could extend this distillation theory here. First one, we called it absolute teacher. It stems from the fact that what we care about is this embedding position in the space. So what we can request of the student network is that it produces exactly the same embedding position as the teacher network. So if the teacher takes one image and says that this image is projected to position 35, 22, 42, the student should also project this image in the same position. And we can penalize the student if it does not and make it learn this way. However, there is a second approach, and it comes from the fact that we don't really care that much about the exact position in the embedding space that the image falls into. What we care about is the neighborhood of the image, because what we want to do is to search for nearby images and return them as similars. So maybe we don't need to penalize the student network if it doesn't produce exactly the same embedding. We have to penalize it if it doesn't assign the same distance between pairs of images. And using this approach, then if for a couple of images the distance produced by the student is very different from the distance produced by the teacher, we will have to make the student learn a bit more and produce a similar organization of the images in the embedding space. So we tried both approaches, and we found that both of them improve with respect to training the student only with the hard labels in our dataset. And actually, the relative teacher produces much better results than the absolute teacher. So allowing some flexibility to the student to reorganize a bit the space as long as the things are projected in the same way seems to work pretty well. This work was submitted to CVPR, and we have learned this week that it has been accepted. So we are very happy about that. And to conclude, I will say that network distillation is a technique that works very well to compress already good networks to a smaller size. And in practice, in our case, we have been able to reduce about 1 order of magnitude the parameters of the network, and that reduced the cost for the company about 20%, which is quite significant in our case. And also, one extra benefit of network distillation is that as we only need now the predictions that the teacher makes, we are allowed to use any amount of unlabeled data that we have or we can get our hands on. So basically, we can train our student network with unlimited amounts of data and hopefully give it a lot more robustness to generalization. And beyond that, what I would like to convey also is that fashion data is a great playground for computer vision. There is a lot of data out there, and it is really fine-grained, very structured. And there are many, many tasks that are really interesting to try there and that are also useful for companies. So they are willing to invest in them. And also, it's a very human-centric thing. So anything that you can think about humans, for example, predicting pose or detecting them is also useful for fashion tasks. And finally, the last thing I would like to say is that interesting science can be done even in small startups. And the government has many programs to help to foster collaboration between companies and research institutions. So you have plenty of top-level scientists at your disposal if you want to do that. And at WIDEYES, we really believe in that. We try to collaborate with several academic research institutions, and we do industrial PhDs, and so on. So that is all from my side. If you have any questions, I will be very glad to answer them.
Jan and I have microphones, so questions, anyone? Otherwise, yeah. Jan, maybe over there. Or you can take this one. Yeah. Thanks. Oh. Yeah. Can you hear me?
Hi. Yeah. Thanks for such an interesting talk. I've seen these network distillation things before, so I've heard about it, never used it. I'm wondering, what criteria do you use to reduce the architecture for the student network versus the teacher network? So how do you decide, or which parameters do you decide to trim in the student one? So
you mean
what's the design change for the smaller network?
Well, you can basically try different architectures and see which one works the best. Basically, you can try to reduce until you start dropping in accuracy or any other metric that you care about. And then, obviously, you probably have to stop reducing the network.
But you mean, for example, a convolutional network.
Right.
You remain with a convolutional network,
yes,
but you
yes.
reduce feature maps. That's like typical criteria, I guess. No receptive field thing, or?
We have not tried changing so greatly the architecture. Usually it's a smaller version of the same style of network. Maybe switching from a BGG to a ResNet, but usually staying within these type of networks. We have also tried very drastic reductions, for example, going from a ResNet 101 to a mobile net. and it also produced good results. Obviously not at the level of the teacher, but still quite significant improvement.
But what if you try that small one with the same label data of the teacher one?
Yeah, so actually you can use any data that you want. So basically the student network will see batches of data that he will have to reproduce the predictions of the teacher networks. Most people, they use at the same time the hard labels to provide an extra supervision signal, and that seems to work better. But you are not restricted or required to do that. You can work with only one objective if you want.
Okay, thank you.
Any more questions? That's it.
I have a couple of questions, actually.
Mm-hmm.
The first one is, how did you deal at the beginning with getting the label data?
Mm-hmm.
Because it seems to me as being one of the key points.
Yeah, it is.
And secondly, for this teacher network,
Mm-hmm.
do you care or do you have some problem by at some point it may lose capability by time? If now you are trusting on its performance to teach to the
Mm-hmm.
student network, but at some point maybe new type of fashion appears or something. I don't know.
Well,
Just
all right. So first, the first question. Yeah, it's critical to get label data, otherwise you can't do anything. So actually, the first thing that you have to do is agree on some taxonomy of classes or attributes or whatever to use. And once you have that, you can start labeling data. In the case of fashion, it's actually quite hard, because usually if you try to be too fine-grained, the differences between things will be too small. And if you try to use then a crowdsourcing approach in which you just send things to Crowdflower or Amazon Mechanical Turk, the annotators will not know the difference between things. So for certain types of pattern types, for example, it's really difficult to distinguish. So usually we also rely on home annotation teams or specific dedicated annotation teams in other annotation providers, and we train them a lot, and then they can really produce labels for us. But yeah, it's really critical to get enough training data. And the second question, if you remind me, was about
the potential decrease on
Sorry.
performance.
So well, you keep training. You can keep training teachers. If you have new data, then you can train better teachers and then train other students for these teachers. And you don't have to limit yourself to a single teacher. You can use an ensemble of them and then combine their approaches. So if you teach, you train different teachers, you can combine all of them and hopefully get better estimates. There is no limit in how expensive the teachers can get, because in the end, the network that really matters is the student network that will go into production. So you can throw everything at the teachers if you want.
I have two questions. One is in the case you pose here about the triplets.
Right.
How sensible is the training process to the balance between the positive and the negatives?
Actually, training these deep metric learning networks is quite hard. It requires a lot of tricks and fine-tuning. And regarding the balance, you mean hard negative mining, maybe, or?
So, well, actually, when you in here, one sample is the three things at the same time. Is what
yes.
Ah, okay.
So you sample the three images and then you forward this. Okay. So the loss is computed in terms of these three images at the same time.
Okay, then I understand. And then another question in the teacher-student thing.
Right.
There are other approaches also, like binary neural networks that you can train also following this teacher-student approach. And these new students are also smaller in terms of memory and faster in terms of speed. But at the end, the usual problem is that the management of the images going through the disk or the camera or whatever to the first layer of the network is the real bottleneck in the current hardware. So did you say, did you compute or evaluate if in your case is really the processing of the networks what matters the most, or was the moving the data around?
Okay, so I think that, I mean, if I understood you correctly, I think you are thinking more on embedded devices that take the images and process them themselves. Our domain is basically the cloud. So we don't take the pictures ourselves. They are sent to us through an API call. But yeah, probably these extra costs of sending data around, they are also important. Our problem was more that if we used very big networks, we cannot put so many networks in every node in the cloud, and then we have to start more nodes, and that is expensive. So rather than really getting the fastest possible speed in processing, is more a matter of the number of computers that we can have at the same time working with one network or the other.
Any questions from the right side? Yeah.
So when you do the triplet loss, right, for the negative cases, do you randomly sample or do you search for any hard cases?
Right. We have tried many things. Randomly sampling is obviously the first thing that we tried. It is pretty hard then to converge, because in the end, all your triplets will be useless. I mean, the negative will be far away from your positive anyway, and the loss will not learn anything from it. We tried hard triplet sampling, but we found that it usually produces degenerate solutions that are really, really overfit to the training set. We also have tried with semi-hard negative sampling. That seems to work a bit better. There are many new things that are published in that space, and we are trying them, but it's a work in progress. We are trying to improve our networks, so it's not finished yet.
Any other questions?
Thank you for a great presentation, and I really want to also say that I think it's very admirable that you're sharing your great work. There are a lot of cool startups here in Barcelona, but not all of them within the field of deep learning also come up on stage and actually share what they're working on. So first of all, thank you for that. Then my question would be, imagine there's someone here in the audience who also have an idea, perhaps within computer vision. They might be researchers and they're thinking about an application. What would the process be to work together with the local government?
Oh, okay. So there are a number of programs that you can apply to. I mean, I am thinking on someone that already has a company, probably, that has established the company, and
that could be the use case, or maybe they haven't started yet.
Okay, if they have not started yet and they are having trouble maybe finding funding or opportunities and so on, it is possible to do spin-offs. The research center are usually interested in finding people who is willing to start a spin-off of the research center that then can turn into a company. And that makes it easier for the interested person, the founder, to start the company. Obviously, they will take a share of the company afterwards, but it's less hard than trying to go yourself to raise the funds to start the company and so on. And they can provide infrastructure and training and manpower even. If you already have the startup, then there are a number of programs that are advertised online in the government web pages. Or if you go to a university and you talk with people there, they will probably be aware of them and they can help you to apply to them. Well, basically that. It's important to have contacts in academia, though, to know what is the relevant people to talk to and what are the things that you can try to do.
So at the end of the event, they should come and tap you on the shoulder if they have any questions, maybe.
Yeah.
Or maybe that's too much.
No,
okay.
I can try to help anyone that wants, but I don't know if I will be able to help them very much.
It makes sense. Yeah.
I want to pressure on that just because I think it's a very relevant question. If you had just graduated from your doctorate and you were to start your company again, would you rather go the spin-off way and fight with not fight/agree with the university government regulation, or would you start a startup and do it from scratch? Okay,
first I would like to point out that I am not a founder of this company. I joined in pretty early, but I wasn't in the initial team that did it. In the particular case of White Ice, it is not a spin-off. They went their separate way from the university. They founded the company themselves. But depends on how brave you are, basically. If you are up to the challenge of raising the funds and finding a place to work and infrastructure and so on, then you probably are better off by doing it by yourself, because you will retain more control on the company and a bigger percentage of it. But you may also fail in a more easy way than if you have the support of a university. So it depends on how brave you are, basically, and the resources that you have.
Okay, let's give a final round of applause.
Thank you.